Okay, and then I think we are good. So hi, everyone. Thank you for joining me here today. The session we have now is on bringing Dask to high performance computing clusters and grids with Jenna Lau-Caruso and Michael Feiman. So Jenna is a software developer on the Spectrum Conductor team at IBM, where she helps customers deploy and manage multi-tenant high-performance Spark and Dask clusters. Over the past 7 years, she has worked on management lifecycle around clusters of these environments, including configuration and deployment of the software stack and integration of Dask as a first-class citizen in the Spectrum Conductor environment. She graduated from York University with a Bachelor of Arts in Computer Science and Creative Writing. Michael has been working on the distributed computing grid, cloud, and big data for the past 25 years on HPC, Hadoop, Spark, and now Dask workload scheduling and resource management architecture. Michael currently works as the principal product architect at IBM on the Spectrum Computing Data and AI, and he holds a master's in electrical engineering. And with that, I will pass it off to the two of you.
Thank you.
Thank you. Hello. So let me share my screen. So I hope you can see my screen. So this talk today, we will talk about bringing Dask to high performance computing, HPC clusters and grids. So we will talk about challenges which we were facing bringing Dask technology to the HPC grids. In particular, resource challenges, because enabling dynamic sharing between CPU and GPU resources need to be done on between multiple clients on different line of businesses. Also, because of this sharing, we should provide a safely reclaim between resources shared by different applications, different users. Another challenge is security. We need to enforce a secure communication across all components in Dask application and in management. And also, we should secure, authenticate a user with underlying authentication system and provided corresponding authorization. Also, administrative challenge with deployment to ensure each Dask cluster on the grid is using the same packages and it's consistent on all hosts, and also synchronize and update configurations on all hosts in the cluster. So this is the very generic diagram of our grid architecture, where we have heterogeneous on-prem or in-cloud hosts, and we're providing Spectrum computing resource management layer, optionally storage, and then on top we onboarding different workload management frameworks. We have batch for LSF, SOA with Symphony, and now the conductor is bringing new technologies such as Spark and currently Dask into this grid environment. So we will be talking more about this onboarding part of the Dask and also the challenges I listed before. But from the user experience in multi-tenant environment should be simple. Each user actually needs to have its own, each tenant needs to have its own environment shared by multiple users. So we have multi-tenant and multi-user environment. And in that tenant environments, they need to have ability to onboard different types of workload framework systems, as well as packages, for example, using Anaconda environment, also interactive things like Jupyter notebooks. And overall, the cluster will be sharing a number of such tenants. Each of them has different workload components, and also different combinations and of these components and providing central security for all the users. So we should ensure data isolation for these users, and at the same time to do a dynamic sharing of the resources between them. To do this, we providing in the grid generic instance group as a way to define this tenant. So it has a component based design. Basically, can have built-in components, and also it's provide a way to add additional custom components. So components can be divided in few different groups. So workload components like Spark, Dask, and notebooks like Jupyter or Studio or some other interactive custom components. And then the environment like Anaconda, Conda environments, and connectors to different data sources. So the components service run as distributed long-running services, and we providing security. So here on the right side, you can see this is the building components, and here we see the Dask as a newly introduced component. So Jenna will now discuss in more details what we're doing with Dask technology and how we're bringing it to the grid.
Thanks, Michael. So this picture here illustrates the architecture that we have for onboarding Dask onto our grid. So you see at the bottom here, we have our resource scheduler, which sort of represents our grid. We've introduced a new Dask manager service. This is a long-running service that runs within the context of one of those instance groups, and it acts as a client between our distributed scheduler and the resource scheduler. We've also introduced a new Dask cluster type, which is called the conductor cluster, and it contains a scheduler plugin in it, which helps to interface with the Dask manager service. So the idea is that when a Dask distributed scheduler needs workers, it would first request resources from the Dask manager, which would proxy that request to the conductor resource scheduler. And then once the resource scheduler has allocated resources, it would help to launch the appropriate worker, whether that's a Dask worker for CPU workload or a Dask CUDA worker for GPU workload. And then it also facilitates some communication from this Dask manager client back to the scheduler in the case that resources from the cluster need to be reclaimed for other workload. So I'll talk about that a little bit later as well. Can you go to the next slide? So we'll take a little bit of a closer look at each of these services. The Dask manager service is facilitating communication both through REST, so it's accepting REST communication from the distributed scheduler, and it's communicating back to the scheduler using the Dask TCP communication protocol. It's doing that by using the scheduler plugin and the diagnostic handlers to facilitate that communication. It also adds an authentication and authorization layer to provide that authentication with the common role-based access control within the cluster. It's SSL enabled, and as I mentioned, it's acting as a client between these two systems. The conductor cluster, which is our new Dask cluster type, is the hook in the user's application code. What happens when you create a conductor cluster within your application is that it creates a scheduler first locally. It then registers with the Dask manager, authenticates, and provides all of its worker specifications. And then it also implements the smart reclaim logic to handle retiring workers without requiring us to run tasks. The Dask workers themselves run as what we call activities on the cluster. So they can be defined to occupy either one slot, which typically would map to one CPU or GPU, or they can be defined to occupy more than one slot, depending on the workload requirements. They can also be defined to be CPU or GPU, and the Dask manager will handle toggling which Dask worker command needs to be started in either case. Next slide. Okay, so I'm going to walk through each of the challenges that Michael introduced one by one so we can see how they're addressed in this system. The first set of challenges related to resource scheduling, and specifically the sharing of resources and the reclaiming of resources between tenants and between applications. So within our grid, we represent each tenant and the breakdown of applications within the tenant in a tree-like structure. And what this allows is the administrator to create a resource policy and define resource sharing constraints and requirements between the different tenants based on priority of different tenants and whatnot. Each Dask application within this model runs as its own leaf within the tree. And the result of this is we got two different behaviors for resource scheduling. Within a single tenant, all Dask applications are treated equally. What that means is that we'll get fair share resources between applications within a single instance group. So if you start one application and later say it's taking all the slots that that instance group is allocated, later another application is started, the cluster will actually reclaim resources from the first application and give them to the second application so that they're distributed evenly. The sharing between instance groups, though, relies on the resource policy that's defined on the cluster. And so that may be fair share, or it may be skewed heavier to one tenant or another, depending on the requirements. With the reclaim, we, of course, don't want to be in the middle of running an application and then have a bunch of workers reclaimed and closed and have to rerun a bunch of tasks. So what we've done in the scheduler plugin is we've implemented logic to receive those reclaim requests and first try to identify which worker is the most optimal to close based on how many tasks it's processing and how much it has in memory. And then based on that selection, we request that those workers close gracefully so that they migrate all of their memory out to another worker before closing, which results in avoiding the need to rerun tasks later on. Next slide. The second resource challenge is the mixing of CPU and GPU workload in a way that we can switch between these depending on what the application needs in a fairly transparent and easy way. So when you create an instance group and you add Dask to that instance group, you can pick a resource group for CPU and a resource group for GPU. And as I mentioned, the way that the slots are considered on both of these are independent to the type of resource group that you're defining. When you configure the instance group, you can set a default workload type. So you can pick CPU or GPU as default, but the application code can, of course, override it to specify what their needs are. Depending on which is specified, the Dask manager will select the right resource group to run on. It will also select the right worker command and the applicable arguments when starting that. So all the user has to worry about is specifying my application needs GPU or my application needs CPU, and the Dask manager and the cluster is handling the rest of it. Under the covers, the resource scheduler does do some extra handling for GPU resources to ensure that workload is only running on specific devices that have been allocated, but I'll leave the details to that for Michael to go through in the demo later. Next slide. The next set of challenges is related to security. So the first one being SSL. Anybody who's managed a very large cluster and lots of different types of workload will know that configuring SSL certificates and managing them across the cluster and across each of the different workload types can be very complicated. What we have in our grid is a common SSL management layer for all of the workloads. So the administrator only has to create one set of tiered SSL certificates, and the cluster is configured to know which set of certificates to use for which workload. And it's managed consistently across all the different workload types. The second challenge for SSL is the enforcement. We don't want to define all our certificates on our instance group and then have somebody start up a Dask scheduler and not specify the certificate information and just run workload on the cluster that's not secured. So this is actually controlled at the instance group level and enforced by the Dask manager. So once an administrator has indicated that SSL is required or enabled for an instance group, the Dask manager will actually reject any scheduler that's trying to connect without the required certificates. Finally, there's a challenge for SSL on the application developer side, which is that they require right now the location of all of the different certificate pieces, and they require this information on all of the hosts where the workload will be running. In reality, most application developers don't actually have access to the hosts in the cluster. They don't know where the certificates are on the host where the workers are going to be running. So our solution here is that the Dask manager is handling all of the certificate information for the workers that are running on the cluster. What this means is that if an application developer is working within a notebook on the cluster, they actually don't need to care about SSL at all. Everything will be handled for them completely transparently. If they happen to be working outside of the notebooks or even outside of the cluster to launch the application, they only need to worry about their local certificate and local key files. And then once they connect to the cluster, the Dask manager will handle the worker side. Next slide. Our second security challenge is around authentication and authorization. So we want to ensure both that only users who are authorized to use the cluster can use it, that they're only using the resources that they're allowed to use, and also that within the cluster that workload is running as a correct user to ensure data isolation. So for the first, the authorization concern, we've implemented an authorization authentication layer within the Dask manager. So as I mentioned, the scheduler needs to register with the Dask manager to connect to the cluster. And part of this registration is actually performing that role-based access control and rejecting any user that's not allowed to connect to the cluster. In terms of the operating system user that's used to run the Dask workers, we have some flexibility here in our configuration. If an administrator has enabled impersonation for the instance group, this means that all of the Dask workers are going to run as the authenticated user on the operating system. Whereas if impersonation is not enabled for an instance group, the Dask workers are going to run as a predetermined user for that instance group. So you potentially have isolation of data per user or isolation of data per tenant, depending on how the configuration is done. Next slide. Finally, we'll go through the deployment challenges. The first one being package version consistency. Anybody who's troubleshooted a large Conda environment can tell you that if the Conda version, if the Conda packages are incompatible or get out of sync, they can create a whole array of different problems, and they can be very difficult to debug. If you add to that a very large grid where maybe packages are only out of sync on one host, the problem becomes even more complicated. So what we do within Conductor is that we use an Anaconda management flow, which allows you to define different Conda environments which are associated to a set of hosts. When you add packages or update packages to any of these Conda environments, they're automatically pushed out and synchronized on all of the hosts in those resource groups. So we ensure that all of the hosts remain in sync. In addition to that, you can associate a Conda environment with a specific tenant in terms of access. You can also associate it to a specific instance group, a specific workload type. So you can associate a Conda environment to an instance group overall, or to just the Dask component of an instance group, or just the notebook component of an instance group. And this ensures that all workload of that type is going to use the same Conda environment within that tenant. And more importantly, the same Conda package versions for all of the workload within that tenant. Next slide. Lastly, we address the configuration issues. So by treating Dask as a first-class citizen within the instance group, we actually expose all of the configuration that we support for Dask right within the GUI. And we allow the administrator to configure there both the security configuration and the workload configuration for the workers. Security configuration is treated as enforced by the Dask manager. So all the security information that's configured here cannot be changed by the workload or by the application. But workload configuration here is treated as a default. So the administrator can set, for example, a default workload type as CPU or GPU. They could set a default memory limit, maybe as 50 gigabytes. But if the application required more or less or a different workload type, then they would be able to set that when the application code is running. Next slide. This slide just shows a little bit of our Conductor cluster options here. What we've done with the Conductor cluster is to implement the job queue cluster from the Dask job queue project. And basically, once this is instantiated and registered with the Dask manager, you can connect a client to it and use it just as you would any other Dask cluster. Next slide. We also have a tight integration with Jupyter notebooks within the context of an instance group. So you might notice in the screenshot in the first cell here, the Conductor cluster is initialized with no parameters at all, which means that the username password authentication mechanism, the SSL information, and all of the default configuration is all handled automatically. So the user doesn't have to worry about any of it. They just pick it up and can get started right away. Next slide. And then finally, of course, we support running a Dask application outside of the notebook as well. So if users running within the cluster, they can point their Dask root config environment variable to the deployment directory of their instance group. This will allow them to pick up all of those default configurations that we were talking about. And if they're running outside of the cluster, they can either export this configuration or can specify it explicitly. And we provide several convenience options to handle the authentication and also to handle the Dask manager address, either by providing it explicitly or providing just the cluster address and the instance group name and allowing it to be looked up. I'm now going to pass it back to Michael for a demo.
Thank you, Jenna. So let me go to the cluster. So here you can see this is the conductor, sorry, conductor cluster dashboard. All right, so we have here 3 hosts. 2 of them has only CPU and 1 GPU. So we can also demonstrate how Dask working with GPU devices. And going to the instance groups, so I have here created 1 instance group, but in general it's multi-tenant, right? So it can be dozens or even hundreds different tenants. And just a little bit on configuration. So this is how instance group is configured. So it has a basic setting with the deployments, local deployments or shared deployments, and then general parameters like a security enablement. And then the components can be Notebook, Spark, Dask, or some additional custom components. So if we're talking about Dask model, so here we provide configuration specific for this implementation of Dask integration. So for example, by default, we're using an adaptive plugin to the Dask scheduler, and we are scaling the Dask worker to 0. So basically, when no workloads, there is no workers to be started, and I will demonstrate it later. And so on, it's a number of parameters which can be specified per instance group. But also, most of these parameters can be also specified in the application. So they overwriting the defaults for that specific application for its scheduler, which communicate with Dask Manager. So then we have also Dask instance groups usage parameters, and we can open the Dask Manager UI, which is basically I already have it. So you can see now that this is empty because we didn't start any applications yet. And so we will return to this to show how it's running application. In the same time, in the same instance group, we have integrated multiple notebooks. So it's as easy as just specify which user assigned which Jupyter server, and we will create this Jupyter server, and it will run on the cluster. So I have now 2 users, admin and user B, having their own notebooks. So if I switch to that user, this is in notebooks. We also onboarded Dask Jupyter Lab extension, so we can see how it's running. So first, this is just a classical example, and we will just run it all. And when we creating the cluster, we can see that we had 0 workers, and then the number of workers is growing based on workload. And in the end, we go back to the 0 workers. So one change which user application need to have is need to have this conductor cluster instantiated. It can have multiple parameters. So here I'm saying that each of my workers will have 2 GB memory limit. And I also pin in the dashboard, so we can specify it here. And as soon as the client created, then the application is just a regular Dask application. Also, as Jenna showed in this slide, we're providing helper, which give all the potential parameters which can be used, but when you submitting it from the integrated notebook, like here, it basically can run without parameters, and it automatically knows where to connect to which Dask manager. So another example I want to show is related to GPUs, right? So this is, let me just run it and we can talk. So this is the Dask XGBoost. So the only difference is that we specified here, sorry, let me go to the beginning. All right, so this is Dask XGBoost. The only difference is to specify here that it will be a GPU type. All right, that Conductor automatically will provide GPU resources through this Dask manager. So Dask manager will request resources from the GPU resource groups. And here we have basically only 2 GPUs. So each worker is 1 GPU device. And you can see that this is also dynamic. So when this running application doesn't need both, then it will be using the minimum. And it's also using part CPU, part GPU. So we can see here that currently utilization is low, but when it's come to the state where it will be doing actual training, then it will be allocating whole GPU. So just to show this, so currently it's going to the training. This is Dask XGBoost training. You can see that it's occupying memory, and in a moment it will be also occupying, oops, running into some error. But basic idea is that it will be occupying a GPU as well. So let me just clean that. So if we go to this third use case, which I wanted to show, was just related to the showing how we're doing reclaim. So first, let's clean that. Right. So here I will start a very simple example, which just using GPUs, CPU, sorry, and we can see here that the only difference that we're saying that it's requires 16 workers, right? So when it's running, it's allocating all the workers to it. Now we had another notebook for user B. So that user, let's say a little bit later, start to running workload. So what will happen here, that it's start to reclaim workers from the first one, right? So if I go back, you can see that now it's taking only 8. So basically it's trying to be fair share. And we have number of workers growing here till it be 50-50. And we can see that it's finished. And now if I go back, I can see that it's again allocated all workers to itself. So it can continue to finish. One important thing here is that we not error any task, right? So I can show here that we have error tasks. So the reclaim was done gracefully. And as Jenna described, that we're basically trying to find first a less loaded worker and then migrate task from it, and only that shut it down. So that concludes my demo part, and I think we're ready to take questions if somebody has any questions.
Great. I did see one question in the chat from, and I will read it, and I think we only have time for one question, so quite good. So on grid environments where the computing nodes are distant, so they're not necessarily in the same network. Have you faced challenges regarding the transmission of the data in those scenarios?
So we normally working with production grids inside the large customer environment, which is can be potentially in different networks and under firewalls. So yeah, it would require a challenge to configure the ports for the Dask listening and then opening it in the firewalls. That's mostly what we encounter. But other than that, it can work with different networks, yes.
Great. Well, thank you both for that session. And with that, I think it is time to move on to the next one. So yeah, thank you both. And if you have more questions, audience, if you have more questions, please go to the Dask Summit Slack. There's been a lot of chat and stuff on there, so that's a great place to keep talking. So thank you.
Thank you.
And so if everyone can give me a second to like switch around all the speakers and stuff, then we'll continue on. So.